Good morning. Just a quick word about myself. I've been in the electron beam and laser welding business for longer than I care to admit, but it's certainly more than 40 years. Designing equipment, solving application problems, and operating job shops in the UK and the US. The presentation is an adaptation of one that I gave at the American Welding Society, and does in fact include more than just a user-friendly electron beam welder. We have a facility just 2 miles from here with 6 electron beam welders and 3 lasers, and we're about to expand the laser capability for higher power applications. This is a very brief overview of the 2 processes, and I will show you as we go along examples of those particular aspects of these techniques which are most appropriate. Both laser and electron beam are high energy density welding processes, and they usually operate by fusion of 2 metals that are placed in intimate contact. Normally there is no additional material added, and therefore with such a fine weld the parts have to fit very well. The equipment that we have includes a 400 watt laser and 2 400 watt lasers and 1 small laser that you can operate by holding the components by hand under the beam. Just a brief introduction as to how the beam is generated. It's a high velocity stream of electrons or a high velocity stream of photons. Fortunately or unfortunately, photons are a lot lighter than electrons, and therefore the capability of electron beam is from the small to the high power end of the welding spectrum. The characteristics are deep, narrow welds or very small conduction welds. The electron beam is generated in an electron gun, the electrons are emitted by a hot tungsten filament and accelerated with a high voltage, travel on down the column until they are focused and deflected by electromagnetic coils. The whole process is done under vacuum because the electrons get dispersed by air molecules, unlike photons. The equipment size that we have ranges from 12-inch cube up to 36-inch cube, and here is an example of such a machine, and the smaller machine are fitted with exactly the same work movement facilities as the big machines, and most of the applications of these processes are in medical and aerospace. I always tell everybody that when they ask me where can it be applied, and I usually tell them anything that's expensive, because obviously the equipment is expensive, and compared with conventional welding it does cost more. But there are ways of optimizing the equipment development started in 1968, and this was the machine, the world's first small electron beam welder, that I developed in 1968. Subsequently, in 2007, this is what it looks like. Touch screen, data recording, online parameter and fault finding, and very rapid evacuation time. The 36-inch cube, as you can see here, is just capable of handling bigger parts or or a large number of small parts. But normally speaking, if you're electron beam welding, you want to put small parts in a small chamber, and the productivity is greater. When the equipment is small, obviously they're fitted with the same sort of devices, and multiple fixturing is one way, even in a small chamber, of welding small parts very quickly. Also, because of the volume consideration with high vacuum, the tooling has to be specially designed. This is something we call big mouth. The reason is that it has a big mouth, and as you can see, it's essentially a two-jaw chuck, but it's very slim and allows you to weld obviously large diameter parts. We do a lot of aircraft components in here where they're long tubes with a large head. Occasionally, when the two materials are incompatible metallurgically or they're prone to cracking, we can add filler material. And this is a typical example of a wire feed system that fits inside the vacuum. This is another piece of specialized tooling which is used in satellite apogee correction rockets. And if you look carefully, you can see at either end of this a weld. These two little bands, one at each end of this component, are the weld. So you can tell how fine and neat the whole thing is. This is a fuel injector for gas turbine engine. Part of the capability of the electron beam is to make thick section welds. Our particular equipment will go up to 700 thousandths of weld penetration in a single pass on stainless steel at 20 inches a minute. It's difficult to see, I know, with all these wonderful lights and everything. It's probably difficult to hear as well with all the machinery, but anyway, this is a pressure vessel. And this is one use of the thick section welding where high strength is required with a low heat affected zone and low distortion. Another application in electron beam and laser welding is the welding of components very close to sensitive non-metals or coils or semiconductors because of the low heat input. These happen to be X-ray tubes, and the welding is quite close to the glass envelope. So that's why conventional welding is not used. The machine performance is very dependent, of course, on the design of the laser and the electron gun. And our equipment that we have in our job shop is the latest. There are support services that we provide for leak testing, metallurgical examination, and I will just mention a little, some further aspects of laser welding. This is a laser welder in operation. Whoop. Welding titanium medical implant components, and we do this on job shop, but we also supply electron beam and laser equipment systems. Another requirement occasionally is for devices that have to be welded in a controlled atmosphere rather than in a controlled shielding atmosphere. The main reason for this is that if you have a component that has to be hermetically sealed and you seal it up, how do you know that it's leak tight? Well, the best way is to ensure that you have a mixture of helium and argon trapped inside, and then expose it to a mass spectrometer, and you can tell whether it's hermetic or not. This is a device that started off as a machine for welding microwave amplifiers for the aerospace industry for just that reason, for hermeticity. There are other ways that we use for ensuring hermetically sealing, which we do on a sterilizable optical component that we finish welding, brazing, and completely finishing the component except for a small hole. That small hole in the component is used for leak testing, and then we resistance weld a small ball into the small hole. 1 second. And the technique of ball sealing, if you haven't come across it, is very elegant, and it's very reliable and very repeatable. So we use that as the last stage in sealing components that, in this case, contain optics and have to be perfectly dry and dust-free. We do the final sealing weld with a 1/16 diameter ball that fits into a little hole recess and is resistance welded. This is a typical type of multiple tooling used in laser welding for spine implants, and each one of those knobs is compressing a component, so you can see that there are multiple components welded in one load. The CNC, of course, just moves from one component to another and does the, in this case, linear welds. The small laser that I referred to is sometimes called a jeweler's laser because jewelers love these things because they can stick their hands under the beam and weld parts. Now, the power is high enough to drill a little hole in your finger, but not dangerous enough that, well, you know, you laugh, but you'd be surprised what some people do. I mean, if you have a lathe, you don't stick your finger in the tool, right? So in the laser, you don't stick your finger under the beam. And you can see with this very clearly if your finger's there or if the component is there. But it's a very, very useful device, relatively inexpensive. These parts that he's welding here are eventually continuously electron beam welded. In this particular case, he's tack welding them so that the tooling becomes a lot simpler. It becomes simpler whether you laser weld it or electron beam, but in this particular case we're using the laser just as a tack welding facility. That really concludes my overview of electron beam and laser welding. The lasers that I've been referring to are YAG lasers, or in a particular case, sometimes a disc laser or a fiber laser. All of these, in that particular wavelength that they generate, are suitable for welding. And I'm only referring to metals. We're not involved in plastic welding at all. The electron beam can be done in either a high vacuum, a low vacuum, and in some very rare cases for the automotive industry in air. But the best welds and the cleanest welds and the welds with the highest integrity are done in a high vacuum. There are many, many specifications, as there are for all of your processes, as to how they're controlled. And electron beam and laser is no different. There are many different specifications, and there are many different audit authorities as well as prime manufacturers who check on the integrity of the welding and the welding operation and the documentation. The great thing about the modern equipment is that it generates its own documentation as you make a weld. So at any time you can reference back if it's required for an analysis of welds that have been made in the past. Just to conclude, I mentioned that our facility is just 2 miles away, and we have a minivan. I know I have 2 visitors. If anybody else would like to come after this lecture, please see me at the back. Thank you for your time.